Before we look at changing the velocity time graph to displacement time graphs and acceleration time graphs, I want you to think about the motion of this object logically. So, whatever object this is, it started at a velocity of +4. So, let's say that's east, for instance. Then it's slowing down, slowing down, slowing down, and here it's stopping. Please remember when it crosses the velocity axis, it is actually stopping because the velocity there is 0. Now, what it's doing here is it's speeding up. It's speeding up because it was 0. You can't go slower than 0. It was 0 and it ends up here at a velocity of -4. It just means it's now, if it was going east there, it's now going west. But it is still speeding up. They often ask you to give the portions where the object is speeding up and where the object is slowing down. Now, if you look here, the velocity is constant, so therefore there will be no acceleration for that little bit. If we go and look at this one here, please do not say that the object is speeding up because here it was going at -4 meters per second and here it's going at 0. And as I said before, you can't go slower than 0. So if you're reaching 0, you have slowed it down. So for this bit, the object is actually slowing down, but it is still traveling west. Here, there's no velocity. If there's no velocity, the object is standing still. That I think you know. If we look here, it's again going from 0 all the way up to that value of 4 again. So now it's speeding up to a velocity of 4 and it's going east again. Please remember for these bits, it's not standing still. It just means that the velocity stays constant at 4 meters per second. So again, there will be no acceleration. So when you get a question like this, always ask yourself logically, what is this object doing? So that's the first thing that we go through. And you can go and look at this slowly later, but I've basically gone through it already. Backwards, forwards, east, west, whatever the question is giving you. Normally in a question like this, they will tell you a direction. So they will say north, east, south, west, or they'll give you a bearing. But normally they use the normal directions, north, east, south, and west. All right, so now we've made sense of this object. The next step to go to our acceleration time graph that I said is the easiest one that we're going to do first, you needed to realize that the gradient of this graph will give you the acceleration. So the gradient, as we said, is equal to acceleration, and you get that by just looking at change in y over change in x. As I said, the gradient values are not always asked. Most of the time, just this, they will mark it off in sections A, B, C, D. But we're going to do this one in detail so that you understand it properly. Now, if I go and get the gradient here, you can see that the gradient is negative. The gradient was negative there where the object was slowing down. The gradient is still negative here where the object is speeding up. So please do not always assume that if there's a negative gradient that the object is slowing down. That is not true, as you can see clearly here. So here we have a negative acceleration. This bit here, we're going to have a 0 acceleration because the velocity stays constant. And we'll actually calculate the real values. I'm going to do it quickly, and then you're going to do an example. Then here the velocity is decreasing to 0, but the acceleration is actually positive because the gradient is positive. If you just stick to what you know, the gradient is the acceleration, then you'll never get these wrong. Here, again, we have a 0 acceleration because there is no gradient and the object is standing still. For this little piece here, it's now speeding up and the acceleration is positive because it's a positive gradient. And again, there we have an acceleration that is 0. So if this was just a sketch graph without values, oops, that's very skew. All you would have to do is just give your labels on the x and the y axis. For the first bit, you need to remember that the times stay exactly the same. So if this value here is 5, 6, 7, 8, then at 8, you're going to have your line negative as a flat line all the way to 8. From 8, there to 14, you're going to have a flat line. The times are normally important because that gives you the intervals. From there to 20, I skipped this little bit, yeah? My times are wrong there. It was this bit here, 10 to 12. So that's a 12. I'm just going to fix it. I'm not going to re-record. And that's then 0. This one is positive. So you're going to have a positive flat line, 0, positive again, and 0 again. So you're just going to have little pieces of flat line. I'm going to do it now properly that you can see. I just wanted you to see that a sketch graph would just look like that. Always little horizontal lines. So let's go and look at the calculation of these values. So for each of these little bits, we would have worked out the acceleration just by plain straightforward getting the gradient. So that bit there, although it's going underneath the line, it's one straight line. It didn't change. So for that whole bit, the acceleration is -1. Here it's +1. The flat bits are all going to be 0. And there we've got +1 again. So if I look at my graph of the acceleration versus time, as I did roughly there for you, it's just going to look like this. Flat lines, horizontal, and parallel to our x-axis. These little lines here, you don't have to draw them, or you can draw them as dotted lines. It really doesn't matter, because all it shows is that there's no time delay between this point and that point. That's really all they are showing. So if you leave them out, it's not the end of the world, because there isn't actually a motion for that little bit. It's just to connect your graph. So they're not really there. You can almost put them in inverted commas. All right, so I think acceleration is straightforward, hoping that you're getting that. Now, the one that normally causes drama is the displacement time graph. Now, again, if you look back at this graph, you need to think, what does the displacement graph give me? So the displacement time graph will give me, the gradient of that graph will give me this graph, will give me the velocity. But the area under this graph will give me the displacement. It's not going to tell you the shape. It's going to tell you the distance that you've traveled, but it's not going to give you the shape. So please, if they don't ask values, don't worry about the values, just worry about the direction. This was above the line, so that would be east again. All of this. Now, when we say area under the line, remember we mean between our line and our x-axis. This little bit will all be west. And then split it up into areas that you can work out easily. So there's a triangle there, and there's a block there, and these will again be east. Now you can think for yourself, is the object going to end up further than it's backwards from where it started or not, by quickly looking at these values? So if the question was a detailed question where you have to work out the values, you would go and work them out. For each of these portions, you would go and work out a displacement. Here again, you're welcome to use it, the shape, the formula for the shape, but I would just go and split it up into areas that I can easily work out. So triangle, rectangle, triangle, instead of trying to use trapeziums and things. But as I say, up to you. So step 1, if this is a detailed question, is to go and get these areas, because those are going to be your plots on your displacement time graph. So I don't want to spend time doing that. So if you look at this slide here, the values have already been calculated. So you can look. For the first bit here, we have 8 meters. So we've traveled 8 meters forward or east, or whatever the question tells you. This little triangle here is -8. But remember, we first went forward and then backwards. So if you look at the cumulative distance here, we start at that point there, then we've traveled nothing. Then from 4 to 6, from 4 at 4 seconds, we've traveled 8 meters, then -8 meters, which brings us back where we started, and that's what you need to remember. Then we're going still west or backwards. And this area here is then 16. So we're now at west 16 or minus 16, and another piece backwards, minus 8. Then we're going nowhere, because if the velocity is 0, it means the object is standing still. So for this piece, there is no area, so there is also no displacement. Then for this area here, we now have 8 meters again. So now we're going back east or forward, and then a whole 24 forward. So if you look at the cumulative distances, I think you can all do the areas, and you are going to practice one of these. Now, if we look at the distances here, after these times, this is where we're going to end up. So now you can also plan your graph, because you can see the highest I'm going to go on on the positive side is going to be plus 8, but I need to leave space all the way to minus 24 on the bottom of my graph. So if you choose a scale, you can choose it, but normally these graphs are sketch graphs and they don't have to be drawn to scale. So you can just put in values as we go. So this is exactly what we're going to do now. We're going to plot these points on the graph. This is a very detailed one. I think I've said it 5 times already. Normally, you'll just be interested in the shapes. So here's our graph. I just emptied it out. So now to plot the displacement time graph, all you're going to do is you're going to plot points. Don't worry about the shape yet. Just go and put your points, because now you know after 4 seconds, we've traveled about 8 meters. So my scale is a bit weird, 5, 10, 15, 20, 25. So it's about there. So these are sketch graphs. Remember, we're not going to check the detail of them. So there we go. Then we're going to go all the way back to 0 at 8 seconds. So make a little cross at 0. Then we're going to end up at minus 16, and that is here at 12 seconds. So here at 12 seconds, we're going to end up at around minus 16. Then we're going another 8 negative, so we're going to end up at minus 24, and that is after 16 seconds. We're going to be at minus 24. Then there was a positive displacement, so we end up back at plus 16. And that is after 24 seconds. Oh, not plus 16, we're adding it up and we end up back at minus 16. And then we go all the way another 24 meters up, which brings us back to plus 8. So I end up at 30 seconds, I end up at plus 8. So that's around there again. So almost parallel to my first point. Now, this doesn't look like much, but it gives you most of your marks already, because now all we have to do is go and look at the shape to decide on the shape. We have to go look on the gradient, look at the gradient of the velocity time graph. Because remember, the gradient of this graph, and this is where it's super important, the gradient of this graph is going to be the velocity. So if we go back and we look at this velocity time graph, here, all the way from there to there, you need to think, what is my velocity doing? My velocity was positive there, and my velocity becomes 0. So that means my gradient must start positive and become 0. Now remember, we're looking at the actual velocity values, not at the gradient. My actual value here was plus 4, and here it's 0. So my velocity went from 4 to 0, so it was positive and it becomes 0. So if I look at my shape of this graph, it must start positive. You know, gradient positive means it's a line up, but then it must become 0. My line is a bit wonky, but I'm hoping you can see the idea. Now, looking back again, so just for doing that shape all the way there, you get your mark. I have a shortcut, and I always say to myself, if the velocity time graph goes down, then my displacement time graph will frown. It always works like that. Now, if you look at this little bit, here we're going down still, so I'm still going to frown, but my velocity goes here from 0 to a negative value of 4. So my gradient must do that. Always say to yourself, whatever the gradient is doing is what the velocity is doing. So it starts from 0, which is a flat line, and it must become negative all the way to that point. No one's going to take marks off you if it's a bit wonky. So I will still get marks for this. Now, going back to our displacement, to our velocity again. Now we need to look at what's happening here. My velocity is constant, not 0, constant. My velocity is constant at -4. So a constant negative velocity means I need a constant negative gradient. And you're going to just keep on thinking like that. Now, please remember, if it's a constant negative gradient, take your ruler. Even I can draw a straight line if I take a ruler and you draw a straight line from that point to that point that they can clearly see, you know that it's a constant gradient. And there we go. For each of these little pieces, you get a mark. Now we're here. This is what's happening to my velocity. It's going negative to 0. So again, my gradient must go negative to 0. I'm hoping you're seeing the pattern. So my gradient needs to be negative, and it is negative here. So negative to a flat line where it is 0. Going to go a little bit faster. Now, as it's 0 there, now this time the velocity stays 0. So if the velocity is 0, my gradient must be 0. So that means flat line all the way to 20. And then from 20, it goes from 0 to positive again. So let's go. So here, it's going to go there. Yeah, where it was, I missed this, but I missed that bit. No, it was constant. Then it's going until it's negative to 0, negative to 0. And then, yeah, this is the bit that I missed. Oh, see, that's the bit that I misplotted. And once this happened, you can always fix it, which is nice, because I just missed that point. So here, it's going to be at 20 seconds. There was a cross missing, but you can see it when you go to your graph and now plot. I could clearly see my mistake because we said the object is standing still. So therefore, my gradient must be 0. Just talking about that one again, I've spoken about it. Yeah, the velocity is 0. So my gradient must be 0. So it's a flat line. Going back, I hope you don't get seasick, yeah? Now it's going from 0 to positive. Let's do that. 0, which is a flat line, to positive. And let's just see how long that's going to happen. It's 0 to positive all the way here to 24 seconds. So 0 to positive all the way to 24 seconds. And there's a dot missing there at 16. So that's the one, that's the one I had earlier. So it's going to go to 16. And then we're going to go all the way to +8. But now again, the velocity is constant. Flat line there. So I should actually just go back to this one. There, my velocity is constant. So therefore, again, my gradient is constant. And you should tell yourself, constant gradient, get my ruler out, because a constant gradient means a straight line, not a flat line, a straight line. And then you draw your straight line all the way there. Now, I know mine is a bit wonky. I've got a nice one for you, but I want you to see the method. Go and do the plots first, and then bit by bit, look at the shape. And I'm going to do my shortcut quickly for you, because you will see now. Let's copy this one across quickly. And you will see now that the frown smile method works very nicely as just a way to check that you've done it correctly. So let's make this a little bit smaller here. And you can quickly see here, what I'm talking about here is this one going down, this one is frowning with the one side of the frown. This one going down, it's still frowning. If it's flat, it's a straight line. Now here it's going up, this one is forming a smile. This one is flat, straight line. There it's going up, this one is smiling, flat, straight line. So just to quickly check if your values are right. Now, this is a bit of a nicer one, so it's still the same, just a prettier graph, and you can check your values. So if you want to practice this from scratch again, you have this video, so you can always go back and go to the first graph and see if you can draw this bit by bit. As I say, if you can do this one, there's nothing we can ask you that you can't do. This is as hard as it gets before we do vertical motion.